Hello everyone, welcome to my channel. In this video I'll be looking at physics and, to be specific, work, energy and power, and this is lesson 1. If you're new to this channel, please don't forget to subscribe. Right, so let's start then. We're starting with work, taking us to the next page. I want to start by looking at work. So work, how do we define work? So let's call this page 1 then. Work is defined, let's start with the definition. Work is defined as is the product of force applied on an object and the distance that the object moves in the direction of applied force. So that's the definition of work. It's the product of force applied on an object and the distance that the object moves in the direction of applied force. So let's look at the SI unit, or perhaps maybe I should start with the symbol. The symbol for work this is for the symbol for work is capital W. Let's look at the mathematical definition then. Mathematically, how do we define work? Well, let's consider a block being pulled to the right or dragged to the right on a horizontal surface by a force F. Let's call it applied force. So we're just going to call it F. And this force is at an angle of theta to the horizontal or from the horizontal. And let's say this block moves through a distance of delta x to that position. This force is still acting there, F, and the angle remains theta. Let's say that this distance here is delta x. By definition, work done by this force F on this block in moving it from this point to that point is going to be force, a component of this force in the horizontal direction. Because remember, the definition says it is the product of work of force applied on an object and the distance that the object moves in the direction of applied force. So it will be the horizontal component of this one, this force that does work on the block. So therefore, we need to draw a triangle here that shows the horizontal component of that force. Let's call this Fx. Not very clearly seen there. Let me use a darker marker. Let's call this Fx. And then we have a vertical component there, Fy. We don't need a vertical component in this case because we're looking at the block moving from this point to that point horizontally. Right. So we're going to say now, by looking at the cosine ratio, you'll agree with me that Fx will be equal to just F times cosine of the angle theta. And looking at the mathematical definition, looking at the definition there of work done, we can say that work done is going to be equal to force applied. In this case, we know that it's a horizontal component times the distance that the object moves in the direction of applied force. But what is Fx? This is Fx. So we take this and substitute in that place. So therefore we can say that work done is going to be equal to F cos theta times delta x. This is the mathematical definition of work done. And we have to say that W is work done, obviously. F is the applied force. And cos theta, theta is the angle between the applied force and the direction of motion, and delta x is the distance that the block moves in the direction of this component of our force F, which is our Fx. If you check in the diagram here, I called it Fx. That's the horizontal component of F in which drags the object from this point to that point there. So that will be the mathematical definition of work. Let's look at the SI unit then of work. So SI unit of work, we're going to look at, of course, remember cosine is a ratio and therefore it has no units. So if we want to look at the SI unit of work, we have to look at force and the distance that the object moves in the direction of applied force. Now, let's put in page number 2. I'm going to page 2 now. Page 2 here. Now, page 2, we are going to look at this one here. Now, I'm saying, what is the SI unit of work? So, SI unit of work. Let me just clean this up a little bit. SI unit of work. Remember the formula says work done on an object equals force times cos theta times delta x. And what are we saying? Theta is the angle between the applied force and the direction of motion. F is applied force and delta x the distance the object moves. Right, so SI unit of W, I'm going to write it like this from the formula there. Hopefully you can see, yeah, you can. So it's going to be equal to SI unit of what? Of force times SI unit of what? Of distance traveled or moved. This is SI unit and that's SI unit. I'm basically saying SI unit there. If you like, let me just put unit there. SI unit, and here I'm also saying SI unit. Right. So now, what is SI unit of the force? Remember, force is measured in newtons. So the SI unit of force is actually Newton. And then we're multiplying by SI unit of distance is actually meter. So we're basically saying work done should be measured in Newton meters. And we understand that we know that work is done in joules. So this Newton meter is actually what we call a joule. J. So what are we saying? Therefore, 1 joule is actually equal to 1 Newton meter. This is critical because we're going to look at calculations involving work. We would have to use the joule there as the SI unit of our work done. Of course, we know that 1 joule equals 1 Newton meter, as you can see from here. Right, so I want to talk about 4 special cases, maybe 3 special cases. Case 1, when theta is equal to 0. This is when the applied force is in the horizontal position and it's in the direction of motion of the block. So for example, we are basically saying that the block is sitting or is placed on a horizontal surface, and this block is being dragged to the right by a force which is horizontal also, F. In this case, theta is going to be equal to 0 because the angle between applied force and direction of motion will be 0 in this case. So how does the formula change then? We are going to say work done equals F cos of theta times delta x. Assuming this block moves through a distance of delta x, maybe up to somewhere here. Yeah, I'm going to just do this like so. Delta x from there up to there moves through a distance of delta x. Now, what is our theta? Our theta is 0. So this is going to be f cosine of 0, cosine of 0 delta x, and cosine of 0 is 1. So this just simplifies to f times delta x, which again agrees with the definition of work done on an object as the product of force applied and the distance the object moves in the direction of force, or in the direction of applied force. So this block here moves from here to there in the direction of applied force. So this answer here, or our formula, agrees with the definition at the beginning here on page 1. How did we define work? It's a product of the force applied on an object and the distance that object moves in the direction of applied force. So remember that all the time. Right, so that's case 1, theta equals 0. Very famous case, but let's look at theta equals 90 degrees. I'm basically looking at 3 cases, 0, 90, and 180. Other cases will come as we move forward. Now, let's look at case 2. Case 2, let me have it on this diagram here, and this is going to be on this page. Let's call it page 3. Case 2, and what are we saying? Theta equals 90 degrees. Let's look at a case where theta equals 90 degrees. So suppose someone is carrying a bag of cement or a bag of some stuff on the head. You're carrying something there. And what are you doing? You're moving through a distance of delta x. So this block, which is being carried on the head, the force applied on it is in a vertical position that way. The direction of motion is to the right. That would be direction of motion. What is the angle between applied force F and the direction of motion? The angle is 90 degrees. So our theta equals 90 degrees. So this, remember, when the block, whatever it is sitting on your head, it exerts a force in the downward direction, the force of gravity. And therefore your head up exerts a force on the block, which is the normal force up. So this F here is actually our normal force, which is our applied force in this case, to balance the gravitational force that the block exerts on your head. But this block moves horizontally. So you are somewhere around here, and the block is on your head. And so what are we saying then? What is work done? Well, the definition says work done equals force times cosine of the angle, that's theta, angle between applied force and the direction of motion, remember that, and times the distance covered. Now, this is F times cosine of 90 degrees times delta x. And what is cosine of 90? The answer is 0. So this is F times 0 times delta x, and the answer is 0. So in physics, we're very specific and very particular. Notice that you may have moved from this point to that point and very tired by the end of the day and having done no work. So we do not confuse tiredness with doing work. You can be very tired doing nothing in physics, and that makes sense from this example here when theta equals 90 degrees. Right. Let's look at case number 3 where theta equals 180 degrees, taking us to page 4. Case 3, I'm going to look at only 3 cases, and we're saying theta equals 180 degrees. So let's look at an example again. You have a block on the surface, and we are saying here that the applied force, this block is going in that direction, but applied force on the block is in that direction. You say, give me an example of such a situation where, suppose you kick a box on a surface. When you kick a box on a rough surface, as the box moves, there's one force acting on the surface in the horizontal direction, and that's frictional force. Of course, we know we have a normal force and gravitational force, but we're talking about horizontal, in the horizontal direction, because this block is moving horizontally. So there will be only one force acting on it, and that's Fk for frictional force. Now, let's say that this moves again through a distance of delta x up to somewhere here. So front to front, that's how we measure distance, or back to back. So that's your delta x. and we are saying there's frictional force there on the surface, Fk. What is the direction of motion? Where is the direction of motion? To the right. Frictional force, the left. The angle between direction of motion and frictional force, if you take this as a straight line, direction of motion there, frictional force in that direction, that angle is going to be 180 degrees. Basically, that's what we're saying up here. So let's look at work done by frictional force, W. I'm going to take this and put it here, Fk, that's work done by frictional force. What are we saying? It's going to be the frictional force by definition times cos theta times delta x. Well, I don't care what the frictional force is, but we know that we can leave it as Fk, and this will be cosine of 180 degrees times delta x. What is cosine of 180? Well, the answer is minus 1. So this is going to be Fk times minus 1 times delta x. And this simplifies to minus Fk delta x. So we can clearly see here that frictional force does negative work on the system or on an object. Why? Because by definition, frictional force is the force that opposes motion of an object and always acts prior to the surface on which the object is moving. I did talk about that in my lesson 1 on Newton's laws. You may wish to go and watch that one because it's going to prove very useful in this topic. Right, so this is case number 3, and frictional force, a special kind of force. It does negative work on the system. It actually reduces the amount of work on the system. All right. Now, having looked at the 3 cases, I want to look at the idea of what we call the net force acting on an object. Net force. So, net force, if there's a force, net force acting on an object, we want to look at work done by net force acting on an object. What is it equal to? Well, let's look at, so I'm basically saying net work, net, not new, net work done on an object. This is a special kind of work. I'm going to come and fix that. Net work done on an object. Suppose we have the following scenario. I have a block here, and let's say that there's a force acting on it. Let's call it F net for network, and this block moves through a distance of delta x up to somewhere here, maybe it's moving from left and continues going to the right hand side, but I'm only interested in observing what happens between point A and point B. So then A becomes my initial position of the block in terms of my observation, and B becomes my final position. So, and therefore, as this block moves to the right, it will have a velocity here, let me call it V initial, and here it will have velocity, let me call it V final. Remember, this block is going to the right. It's going to the right. I don't care what happens there. I don't care what happened before it arrived here, but I'm interested in as it moves from A to B. Let's say mass of this block is M. And let's say that distance is delta x. Right, so we can basically say that W net, that's work done by net force, is going to be equal to, by definition, F net times cos theta times delta x. But remember, now our net force is actually in the direction of motion of the block. So the angle between net force and the direction of motion is actually 0. Direction of motion is along the x-axis or horizontally to the right. So what are we saying? We're basically saying that this is equal to F net times cosine of theta is 0 times delta x. And what is cosine of 0? The answer is 1. So this is actually F net times delta x, because cosine of theta, cosine of 0 is 1. Now, I want to remind you here Let me write this one, W net. I want to remind you something. I'm going to do this. I want to remind you that F net is actually equal to mass times acceleration. That's Newton's second law. F net equals mass times acceleration, and therefore in place of net force or F net, I can put ma. So the formula now therefore changes to ma delta x, because net force equals mass times acceleration. And I want to remind you again on Newton's equations of motion. I want to remind you that we have v final squared equals v initial squared plus 2a delta x. As the block moves from here to there, the relationship between v initial and v final is this one here, where a is acceleration and delta x is that distance there. Now let me solve for a delta x here. I'm going to have v final squared minus v initial squared all over 2. That should be equal to a delta x. If you understand, you can see what I'm simple algebra that I'm doing there. And therefore, in that place, I can actually have a delta x replaced by this expression here. So that gives me, this formula changes to m, and then I'm going to have, watch this, v final squared minus v initial squared over 2, because that is now taking the place of a delta x. Now I'm going to simplify this. My last page was page 4. Yeah, because I ended up with a work done by frictional force here as an example. Case number 3, where the angle between the applied force and the direction of motion is 180 degrees. So here we're saying net work done, right? So now checking me, this is page 5 now, taking me to page 6. Page 6. What am I saying? I want to rewrite this. Remember where we're coming from? We're coming from, let me move this one down, right? Where I'm coming from W net is equal to MA, and our A is this one here. W net equals, of course, W net equals MA delta X, and A delta X. From there, you can see A delta X has been replaced by V final minus V initial over 2. We move this one down, all right? So we have replaced that with this one in that expression there. So we're coming from W net equals this. Hopefully you can see up there, W net. Move this one further down, right? We're moving from here, and I said this is replaced by MA, and then now A delta X is replaced by this expression here to get that. Now I want to simplify this. So W net is actually equal to M, let me say half of M, take 2 out, and then we have V final squared minus V initial squared. So expand this, we're saying W net is equal to half M V final squared minus half M V initial squared. Now notice something, that this is final kinetic energy and that's initial kinetic energy, because kinetic energy is half mv squared. Energy that an object has due to its motion, that's kinetic energy of motion. So we can say that this is Ek final minus, this will be Ek initial, and this is actually change in kinetic energy, delta Ek. So what are we saying? We're saying W net equals delta Ek. This one here is what we call work energy theorem. So this is known as work energy theorem. Very critical in problem solving. Basically, we can state now, they like to pose this in exams, and I have to state it here now. They will say to you, state the work energy theorem in words. because that's the weak energy weak energy theorem formula or equation. But if they say state the weak energy theorem in words, you are going to say work done by a net force acting on an object is equal to object's change in kinetic energy. Or you can say it states that the work done by a net force acting on an object is equal to the object's change in kinetic energy, or is equal to change in kinetic energy of the object. Same thing, right? It states that the work done by a net force acting on an object is equal to the object's change in kinetic energy. You can state it in any way you want, but basically the message is the same. Net work done equals change in kinetic energy. So that's work energy theorem in words. Right, I want to look at one example. Looking at application of this, we are at 26 minutes. Just want to look at one example, and then we will have to come back with many more examples. One example that I want to look at is the following. Combining concepts now. We're combining work energy and power, and I want to throw in momentum and impulse. So here's the question we're having now. It says here that example one, a bullet of mass 200 grams is fired at a stationary block of mass 5 kgs on a smooth surface at A. As you can see here, that's a smooth surface at A. So a bullet of mass 200 grams is fired at a 5 kg block sitting or placed on a smooth surface, and the block is at A, and this block is stationary. The question says so. Stationary block of mass 5 kgs on a smooth surface at A. The bullet strikes the block with a velocity of 500 meters per second, you can see it here, and comes out on the other side with a velocity of 300 meters per second, as you can see. After impact, the block moves from A to B at a constant velocity. After impact, the block moves from A to B at a constant velocity and strikes a rough patch at B. So there we have a rough surface now from B going all the way to C. The question continues and says, as the block moves from B to C, it experiences a constant frictional force and comes to rest at C there, as shown in the diagram. Now we're told here the surface AB is smooth and BC is rough. So AB is smooth, BC is rough. Why is it important for us to know that AB is smooth? So we can actually assume that the system between A and B remains isolated, and therefore we can apply the law of conservation of linear momentum there, because bullet striking a box is an example of a collision. And you know what we do when we're looking at collisions, we apply the law of conservation of linear momentum. Let's look at the questions. Question one, we need this diagram here. I'll put it up here. Question one says, just to remind you, because linear momentum, I covered it some time back, and I did, I think, speak that I was going to incorporate linear momentum in other topics. Work energy and power is one of them. Question 1.1 says, state the principle of conservation of linear momentum in words. So let me state it, and then we are going to look at number 1.2. This is taking me to page, what? At this stage, it's going to be difficult for me to write down the pages. I think I did page, last page was, let me just check here for informative sake. The last page was page number 5, number 6, yeah. Then I'm coming to page 7 now. Fantastic. So page 6 was the last one. Yeah, let's look at page 7. So page 7, I'm gonna call this one page 7, because we're looking at an example now. Let me call this page 7, and then I'm going to call this page 8, and then I'm going to call that page 9. Right, now state the law of conservation or the principle of conservation of linear momentum. Our answers: 1.1, we say that it states that the total linear momentum of an isolated system remains constant or is conserved. The total linear momentum of an isolated system remains constant or is conserved. That's the principle of conservation of linear momentum in words. Number 1.2 says determine the block's velocity between A and B. Remember, the question says between A and B, it moves at a constant velocity here. After impact, the block moves from A to B at a constant velocity. All right, so now we're going to look at conservation of linear momentum. Let me put this one up. We're going to look at conservation of linear momentum. If I put it here, I think you can see it there. Yeah, you can. So I'm now going to say 1.2. I'm going to say checking to the right as positive. That's the first thing you need to do. And then you come and say total final momentum equals total initial momentum. That's the law of conservation of linear momentum. We're talking about the block and the bullet. So I'm going to use BU for bullet, or maybe B for bullet and K block, K for the block. So mass of the bullet, V final of the bullet, plus mass of the block, V final of the block, is equal to mass of the bullet, V initial of the bullet, plus mass of the block, V initial of the block. Let's put in what we know. So we know that mass of the bullet is 200 grams. We must convert it to kilograms by dividing by 1,000. Don't forget that. So this is going to be 200 over 1,000. And then I do this plus mass of the block is 5 kgs, 5. This is going to be, if you check, this is 0.2, 0.2, and then 5. Let's put in the numbers. What is the final velocity of the block? We don't know. That's what the question is asking us to find. If you check here, it says determine the velocity, determine the velocity of the block between A and B. That is after impact. You can see between A and B, it will be after impact there. So we don't know this one, V final of the, this is actually V final of the bullet. We know V final of the bullet is 300. It's for the K, for the block, that we don't know. So let's put in the positive 300 there. What we don't know is this part here, this V final of the block. We're using K for the block. We don't know that. Let's come this side. I'll come back there. V initial of the bullet before impact, that is initial, 500, and it has to be positive 500, because to the right has been taken as positive, and the velocity is actually of the block is to the right hand side, so it has to carry plus sign there. What about a block? Initially, we are told here a bullet of mass 200 grams is fired at a stationary block, so the block is not moving initially. So remember, in physics, most of the information is in the question. So read the question at least 3 times to make sure that you understand and you have all the information that you need for you to answer the question. So this is going to be 0 because the block is stationary initially. And we said that the final velocity of the bullet, it's the velocity after impact, which is 300, and it's also to the right hand side. So it has to be positive 300. Right. This is what we have. Now, the only unknown is this one. Let's perform the calculations. Um, I may actually use a calculator to simplify everything and spend less time. It's gonna be 0.2 this one times 300. 0.2 times 300, the answer is 60. So this is 60 plus 5 V final of the block is equal to 0.2 times 500. 0.2 times 500, it's supposed to be 100. 0.2 times 500 is 100. So this is 100. And that will be 0, obviously. Take 60 to the other side, or subtract 60 from both sides. 5 V final of the block. This is going to be 40 if you subtract 60 from 100. And V final of the block, yes, it's going to be positive 8 meters per second. And to the right. Why am I writing this? Because the question is asking us for velocity, and velocity is a vector quantity. It must have both magnitude and direction. Remember that here it says the block's velocity, not speed. And therefore, you have to make sure that you respect the traditions on how you present vector answers. You must have a plus sign there, magnitude, and direction. So we're done with 1.2. Let's move on to 1.3. This is linear momentum basically. Now 1.3 is where now energy comes in. 1.3 says state work energy theorem in words. I have stated it already, but let me state it again. There is no harm in repeating concepts. 1.3, it states, we're stating work energy theorem. It states that excuse me, the network done on an object is equal to the object's change in kinetic energy. Notice I've stated it slightly differently, but the message is the same. It states that the work done by net force acting on an object is equal to the change in kinetic energy of the object. Same thing. Right, let's go to page 10. Page 10, what are we saying now? Here we go. Maybe the main reason why we have this question is actually found on page 10 and actually on page 8 and question number 1.4. 1.4 says determine work done by frictional force in bringing the block to rest at sea. Work done by frictional force in bringing the block to rest there. It means final velocity is 0. So in order for us to work out work done by frictional force, or whatever case it may be, whenever you are required to determine work done, it is very critical that you draw a free body diagram first, because remember we're dealing with forces here, and it's very important for you to identify the kind of forces you have in your system. So 1.4, remember, let me have the original diagram here. This block, after impact, it slides, it's moving, there's no applied force in that direction. The only force that is acting on this one as it slides to the right hand side along the horizontal direction is going to be frictional force, which opposes motion. Remember, this block is going to the right. Frictional force must be acting to the left, because frictional force opposes motion and is always parallel to the surface on which the object is moving. Of course, we know that there's normal force and there's gravitational force, but those two forces cancel each other out, because this block does not move up and down as it goes to the horizontal surface to the right hand side. At least we can assume that. And therefore, the only force that we're going to focus on is frictional force. And so our free body diagram, like I said, is going to look like this. It's going to look like this. Direction of motion is there, and the angle obviously is 180 degrees. This is your normal force, not important in this case, and this is your Fg, not important. What is important is Fk. So the question is asking us to work out work done by frictional force. Now 1.4.1, we're going to say W, allow me to say WK for frictional force, or I can take the entire FK, put it here, but it doesn't really matter. So I can just say frictional force, or you can write W friction is going to be equal to Fk times cosine of theta times delta x, and we are told that this is actually equal to, if you remember, half mv final squared minus half mv initial squared. What is going to be important is that last part there, not so much this part, because we don't know frictional force. So we're going to say this implies that W, K for work done by frictional force, is just equal to half. What's the mass of the block? Well, it's 5 kgs. What is the final velocity of the block? Well, we're told it comes to rest, it's 0, minus, we're here now, half. What's the mass of the block? 5 kgs. What's the initial velocity of the block? Well, it's going to be the velocity of the block at B. We are told it moves at constant velocity from A to B. And what is that velocity? We calculated it to be 8 meters per second. Here it is. There it is. That should be our initial velocity. It will be velocity at B. You can see velocity at B, and here at C it will be 0 because it comes to rest at C. So we have to square that. So simplifying this is going to be I forgot the mass there. Mass is, oh sorry, I'm squaring 5 instead of squaring 8. Let me just change that because it's a square of velocity. So we're saying we're squaring 8 here, 8, and that has to be squared like that. Fantastic. So this will be 0 obviously, and we're here now. It's going to be half of 5 times 64, so 0.5 times 5 times 64. That's 0.5 times 5 times 64. The answer is 160. So that's minus 160. What is the unit of energy or work done? Joules. Told you at the beginning there when we're looking at the SI unit of work done, the joules. That's work done by frictional force. Remember we said frictional force does negative work on the system. On one of the pages there, it will take me time to go back and show you that frictional force actually does. That was case number 3. Allow me to do that just because I feel it's critical that I show you this. Case number 3, I said, okay, this is case 1. We have case 3. Here we go. This case 3. We said frictional force does negative work. Remember, frictional force and distance covered, these are positive quantities, and then you have a minus there. It means work done by frictional force is actually negative. So this one confirms it. Work done by frictional force is going to be negative. Right. This is our first part. Our second part of the question says, determine the magnitude of frictional force the block experiences between B and C. What we've worked out here is work done by frictional force. Here we need to work out the magnitude of frictional force. What are we going to say? 1.4.2. That will be the end of our lesson for today, at least in this video. We're going to say here, remember, WK, work done by frictional force, or FK, is going to be frictional force times cosine of theta times delta x. This one here, minus 160, we calculated it up there, equals, we don't know frictional force, cosine of, we know the angle is 180 degrees, times delta x. Well, it covers a distance here shown of 5 meters. You can see there, the rough patch is a distance of 5 meters. So that's going to be times 5. Now, this is this 160 equals FK, and times minus 1 times 5. And so we can say that Fk for frictional force magnitude, it will be 1 minus 160 over minus 5, and that should be it should be 32. Let me just check. 160 divided by 5, yeah, 32 newtons. So this is actually 32 newtons. Remember, the question is asking us for magnitude of frictional force. We're not interested in direction, so this is our answer. That means as this block moves from A to B, from B to C, experiences a frictional force of 32 newtons. Notice we had to work out work done by frictional force first, and then we're able to work out frictional force from the very definition of work done on an object. Right, there's another question here which is not posed in here. They can also ask you to work out the coefficient of kinetic friction as the block moves from B to C. But we'll look at that in our next video. I'm going to stop here on this one. If you're new to this channel, like I said at the beginning, don't forget to subscribe. Give us your comments. We truly value your comments. All right, see you next time.